Acid rain is a phenomenon that embodies the complex interplay between human activities and the natural world. Its story begins with invisible gases rising into the atmosphere, borne aloft from factories, vehicles, and power plants. These gases, sulfur dioxide, SO, and nitrogen oxides, NO, mingle with water vapor and oxygen high above the earth. Together, they undergo chemical transformations, forming sulfuric and nitric acids. When rain, snow, or fog falls back to the ground, it carries these acids with it, creating what we know as acid rain. The origins of acid rain are rooted in the Industrial Revolution, a period of rapid technological progress that brought about profound changes in the way humans harnessed energy. Factories and power plants began burning vast quantities of coal and oil, releasing copious amounts of sulfur dioxide and NO into the air. At the time, the concept of acid rain was unknown, and the visible soot and smog were seen as the primary pollutants. However, as industries grew and urban areas expanded, the effects of acid rain began to emerge. Though they often went unnoticed for decades, acid rain does not always fall where the pollution originates. The gases responsible for its formation can travel great distances, carried by wind currents across regions, countries, and even continents. A coal-fired power plant in one area can contribute to acid rain hundreds of miles away, affecting forests, lakes, and communities that may have no direct connection to the source of pollution. This transboundary nature of acid rain makes it a global issue, requiring international cooperation to address. The effects of acid rain on ecosystems are profound and far-reaching. One of the most visible impacts is on aquatic systems such as lakes, rivers, and streams. When acid rain falls into these bodies of water, it lowers their pH levels, making them more acidic. Many aquatic organisms, from fish to amphibians to microscopic plankton, are highly sensitive to changes in pH. As the acidity increases, these species struggle to survive, leading to a decline in biodiversity. Entire ecosystems can be disrupted, with cascading effects on food chains and nutrient cycles. Forests, too, bear the brunt of acid rain. Trees and plants rely on a delicate balance of nutrients in the soil to grow and thrive. Acid rain disrupts this balance by leaching essential nutrients like calcium and magnesium from the soil, leaving it less fertile. Simultaneously, it releases toxic metals such as aluminum, which can damage tree roots and inhibit their ability to absorb water and nutrients. The result is weakened trees that are more susceptible to disease, pests, and environmental stresses. In some regions, the impact of acid rain on forests is stark, with dying trees standing as silent witnesses to the consequences of pollution. Beyond the natural world, acid rain also affects human-made structures. Buildings, monuments, and infrastructure made of limestone, marble, and concrete are particularly vulnerable. The acids in acid rain react with the minerals in these materials, causing them to deteriorate over time. Historic landmarks, some of which have stood for centuries, face accelerated erosion, threatening cultural heritage. The economic cost of repairing and maintaining damaged infrastructure adds another layer to the burden of acid rain. The human impact of acid rain extends to health. Though indirectly, the same pollutants that cause acid rain, sulfur dioxide and NO, are harmful to human health. They contribute to the formation of fine particulate matter and ground-level ozone, which can lead to respiratory problems, cardiovascular issues, and other health concerns. While acid rain itself does not pose a direct threat to human health, the pollutants behind it are a significant public health issue. Understanding the causes of acid rain has been a crucial step in addressing the problem. Scientists and environmentalists have worked tirelessly to trace the sources of sulfur dioxide and NO emissions, using sophisticated monitoring and modeling techniques. Their efforts have provided a clear picture of the link between human activities, such as burning fossil fuels, and the acidification of the environment. This knowledge has paved the way for policy interventions and technological innovations aimed at reducing emissions. One of the most significant steps in combating acid rain has been the implementation of air quality regulations. Countries around the world have introduced laws and agreements to limit sulfur dioxide and NO emissions from industrial and transportation sources. For instance, the Clean Air Act in the United States established programs like the Acid Rain Program, which set emission reduction targets and encouraged the adoption of cleaner technologies. Similar initiatives in Europe and other regions have also contributed to progress in reducing acid rain. Technological advancements have played a vital role in mitigating acid rain. Power plants now use technologies like flue gas desulfurization, also known as scrubbers, to remove sulfur dioxide from their emissions. Vehicles are equipped with catalytic converters that reduce NO emissions. Renewable energy sources, such as wind and solar power, offer cleaner alternatives to fossil fuels, further reducing the pollutants that lead to acid rain. These innovations highlight the potential of human ingenuity to address environmental challenges. Public awareness and education have been key to the fight against acid rain. By understanding the sources and consequences of acid rain, individuals and communities can make informed choices to reduce their impact. Simple actions, such as conserving energy, using public transportation, and supporting clean energy initiatives, contribute to the broader effort to combat acid rain. Environmental campaigns and educational programs have also played a crucial role in mobilizing support for policies and practices that protect the environment. Despite significant progress, the story of acid rain is not over. In some parts of the world, particularly in developing countries, the problem persists due to reliance on high-sulfur fuels and limited environmental regulations. Additionally, the legacy of past acid rain lingers in ecosystems that take decades or even centuries to recover fully. Restoring damaged lakes, forests, and soils is a long-term endeavor that requires ongoing commitment and resources. The fight against acid rain also intersects with broader environmental challenges, such as climate change. Many of the actions taken to reduce sulfur dioxide and NO emissions, such as transitioning to cleaner energy sources, also help mitigate climate change. However, the relationship between these issues is complex, as some measures to reduce greenhouse gases can inadvertently increase acid rain precursors if not carefully managed. Balancing these priorities is a critical aspect of modern environmental policy. Reflecting on the story of acid rain, it becomes clear that it is both a cautionary tale and a testament to the power of collective action. It reminds us of the unintended consequences of industrialization and the importance of sustainable practices. At the same time, it demonstrates how science, technology, and collaboration can address even the most daunting environmental challenges. Acid rain has shaped our understanding of the interconnectedness of the natural world and human society. It has shown us that the actions we take in one place can have far-reaching effects, and that protecting the environment requires a global perspective. As we continue to learn from the lessons of acid rain, we are better equipped to address the environmental challenges of today and tomorrow. In the end, the story of acid rain is one of resilience and hope. It is a reminder that while human activities have the power to harm the environment, they also have the potential to heal and restore it. Through innovation, cooperation, and a commitment to stewardship, we can ensure that the legacy of acid rain becomes a chapter in the broader narrative of environmental recovery and sustainability.